Here it says, on a banked racetrack, the small circular path on which cars can move has a radius of 112 meters, while the largest has a radius of 165 meters. The drawing illustrates the height of the outer wall is 18 meters. Find A, the smallest, and B, the largest speed at which cars can move on this track without relying on friction. Okay, so here's what we have given. So the largest radius, maybe I call it R1, equals negative 165, and the reason is that the car is moving over here into page and being deflected by the centripetal force to the left, so I call it a negative radius, and then R2 here equals negative. Sorry about my R's, but it's a little tough to write on the tablet that I'm using. Okay, this one here is from another another drawing from the book, where they put in the forces for us. So we know, I believe, what the weight is of the car. Actually, no, we don't. Well, let's see. Something interesting must be happening there. So we don't know what the mass is. We don't know what the weight is. What we do know is that the normal force, and that means the vertical component of the normal force, must equal the weight, so that the car doesn't slip up or down but stays on the same level, and that's what has to do with the maximum radius and the maximum speed, and here the minimum speed that it needs to have. Okay, and then part of the normal force, the horizontal component of the normal force, is actually supplying that centripetal force, and notice that at this point the car is circling around to the left, so that normal force is pointing to the left, and therefore that radius also needs to point to the left and being negative. Okay, once again, I like my angles to be measured from the positive horizontal, so theta here, so that the normal force itself is not what is written here, but that the vertical component comes out to Fn times sine of the angle, and the horizontal component comes out to Fn times the cosine of the angle. Notice that whenever I did that, we always used cosine for the horizontal, sine for the vertical. That's why I did it the way I do it. Okay, let's see what we got. Well, we don't know what the speed is. We do know what the radius is. We don't know what the mass is. We, at this point, don't know what the force is. That's kind of interesting. We don't seem to know a whole lot yet. Well, let's see what's happening. Let's write down Newton's second law. Sum of the forces equals mass times acceleration, which of course is a centripetal acceleration. Velocity squared over r. Remember that r here itself is negative. And the sum of the forces here, well, when you look at this diagram, is also going to come out negative. So let's write down the forces. The normal force and the weight are actually the only two forces, equals mass times velocity squared over r. Okay, we need to take them apart into x direction and y direction. Y direction. In the x direction, it's normal force times the cosine of theta plus 0 for the weight equals mass velocity squared over r. And in the y direction, it's normal force sine of theta plus the weight, of course that would be negative, equals mass times, oh no, equals 0, because the car isn't going anywhere in the vertical. Okay, so we have set up Newton's second law, and we still don't know much. Actually, the only thing we really know is the angle here, the angle of the, well, we knew this angle here, In fact, we do know this angle here. Notice that this side here would be 53 meters. And when you calculate that, we come up with 19 degrees. So 19 degrees. And that means that the angle theta that we need is, for the normal force, is 109 degrees. So that angle theta here, and then that angle theta over there. Okay, we will use that cosine and the sine here, but we're supposed to figure out what the velocity is, but we still have that unknown here as well, and technically we also don't know the weight. But so we actually have three unknowns at this point. But let's see what we can do. We take these two equations, we get rid of one of these variables, and they don't even want to know what the normal force is. So we take the second one here, and it's going to say that Fn equals negative weight divided by, or negative W divided by sine theta. Of course, W itself is negative, so it's a negative negative. And now we take this stuff here and we plug it into the other equation. I'm using a different color here. So we're going to have negative W divided by sine theta times cosine theta plus 0 equals mass times velocity squared over r. We still have a couple of unknowns, v and w, but watch what happens. The weight itself is mass times gravity. I'm sorry, negative mass times gravity. And with that negative negative in front of it, let's write it like this. These two negatives will actually cancel out. So what we got now, well, the weight is mass times gravity, and that mass divides, and that was the reason why they didn't actually give us the mass or the weight of the car, because it doesn't matter what car it is, how massive it is, because the outcome would be the same for any kind of car. There is the same maximum speed and same minimum speed for each one of them, so that they wouldn't move out of the curve. Okay, so anyway, this one here then now gives us that velocity equals g times cosine theta times r divided by sine theta and take the square root equals, and there we go. And now the r itself is pointing to the left because it's negative. So it is negative. The cosine theta, it's cosine of 190 degrees, is also negative, so those two negatives take care of each other, and then the g is 9.8, and the sine theta is a positive number, so overall we take the square root of a positive number. And now we have to decide, well, do we have a positive velocity or a negative velocity? Is the car going into the paper, or is it coming out of the page? So let's just say it's going in, so we come up with plus sine, and we have to do it twice. We have to do it once for negative 165 meters and then negative 112 meters. So we're going to come up with two results.